This is video 2 for the waves unit. Let's begin by talking about transverse versus longitudinal waves. So for a transverse wave, the particle motion must be perpendicular to the wave motion. So in this transverse wave, notice that the particles themselves vibrate up and down as the wave moves. So think about taking a rope and swinging the rope up and down. Now this graphic I have here, I like it because it gives you some of the names. So for example, notice that here we have a crest, here we have the trough. The amplitude, we can have positive or negative amplitude, but the amplitude is just from the equilibrium or the zero position up to the top. And then we have our wavelength. So that would be a transverse wave. Some examples of transverse waves would include water. If you were to take a rope and sling it up and down, even some electromagnetic waves. Now we come to longitudinal. Here the particle motion is parallel to the wave motion. So here the particles are going to vibrate back and forth. Now, the region where the particles are smashed together, we call that the compression, and where they're stretched apart, we call that rarefaction. So sometimes longitudinal waves are called compression waves. So compression waves, longitudinal waves, same thing. Notice that we still have a wavelength, and it's just from compression to compression. So that's our wavelength. I can represent a compression wave or a longitudinal wave as a transverse wave. And what I would need to do is I would need to represent the compression as the crest and the rarefaction as the trough. So I can take a longitudinal wave and I can map it over to a transverse wave. Some examples of longitudinal waves then would be earthquakes and sound waves. Tsunamis. These are fun. So a tsunami is a giant wave that hits the coast and washes very far up onto the shore. Tsunamis often destroy buildings that are within a few hundred meters of the beach. Sometimes what causes them will be underwater earthquakes and underwater landslides. These waves have a very high velocity, but they also have a very long wavelength. So in the deep ocean, they may have a very, very low amplitude. So they can travel under a ship without anybody knowing. If you are out in deep water and you're on a boat and a tsunami passes underneath of you, the truth is it's probably some of the calmest water you would ever be on, because it's one gigantic wave that gently lifts the boat up and gently brings it back down, versus a bunch of small choppy waves that quickly lift bob the boat up and down. So a tsunami probably be quite pleasant out in deep water. The problem is, as the tsunami approaches land, they slow down, and that's because the water gets shallow. The energy then is spread out over a smaller depth of water, and as a result, the height or the amplitude of the wave rises. So a typical tsunami will have a wavelength of 10 kilometers. So let's do some math for that. So first off, in deep water, the speed is roughly equal to the square root of the amplitude. So, or I'm sorry, roughly equal to the square root of the wavelength. So if I were to take a look at that wavelength, that's 10 kilometers, or 10,000 meters. So if I were to take the square root of 10,000, I see that the speed is roughly 100 meters per second. Once it reaches shallow water, and what I mean by shallow water is that the depth is less than the wavelength. So when the depth of the water becomes less than 10,000 meters, the velocity is approximately equal to pi times square root of the depth. So basically what happens then is as that becomes smaller, we can see that the velocity is going to slow down. So it's going to become a lot slower than 100 meters per second. What's nice though is that you can outrun a tsunami. So a typical velocity for a tsunami is 171 meters per second. And let's say that our tsunami has a wavelength of 30 kilometers. Velocity for a wave equals the wavelength divided by the period. So what I can do is I can say period equals wavelength divided by velocity. You know, so I can do a little bit of math there. So I take my 30 kilometers, divide that by that, and I get 175 seconds. So what that 175 seconds means is that it takes 175 seconds for that tsunami to pass up through. So in other words, it takes about 87 seconds to rise to the positive amplitude, and then about 87 seconds to fall to the negative amplitude. So basically, once that tsunami hits shore, 175 seconds, you got about 3 minutes. So if you notice a tsunami, if you start running, you have about 3 minutes to outrun it. So if you're young and in shape, chances are you can outrun the tsunami. All right, so I've touched upon some of the math. So let's go, let's put this into a more formal perspective here. So the velocity for a wave will be its wavelength divided by its period. However, remember that frequency equals 1 divided by the period. So, you know, and remember frequency is how many wavelengths pass a point per second. So I can do some substitution. I can see that velocity also equals the wavelength times the frequency. So that's 2 ways of calculating how fast a wave travels. All right, now let's talk about sound again. Sound does not always travel in a straight line. Now sound waves, and really all waves, do not travel in a straight line. They bend. And as a general rule, they bend towards the slow. Think about a marching band trying to march in a parade and go around a turn. The people on the inside of the turn have to slow down, and the people on the outside of the turn have to speed up in order to keep a straight line as they make a turn. Waves do sort of the same thing. So here we have some waves approaching the shore. Now, in the deep water, waves travel quickly. In shallow water, they slow down. So notice that this wave motion, notice how it's bending, and if the waves are coming in at an angle, this side over here is going to hit the shallow water first and slow down. So this side would be the slow side. This side would still be fast. And notice how those waves are bending toward the slow. So as a general rule, waves always come in parallel to the beach. Let's say I have some waves coming in, and this is kind of like an example of light here. So let's say this is some glass, and this is air. Light travels faster through air than it does through glass. So as the light travels, once it strikes the surface, this part slows down first, and it causes the light to bend. And notice how it's bending toward the slow. And sound does the same thing. So water, light, sound, they all do this. All right. Normally, the air close to the ground is warm, and then it cools down as you get higher off of the ground. Well, sound travels slower in cold air than it does through warm air. Remember that as you speed up the air, you speed up the sound. So let's say someone is trying to give a command to their dog, and the dog's pretty far away. The sound waves from the person would naturally bend up. So if these are like my sound waves, or the compressions from my sound waves, I would see that it bends up. So the dog would never hear those commands. And that's how it normally is. Whenever you talk, your sound has a natural tendency to drift up. After the sun sets, the ground is going to cool off faster than the air above. That's because the ground is a better conductor than air is. So this creates something called a temperature inversion. And what that causes your sound to do is bend down. And notice how, it's the cool and the warm, they've switched. It's been inverted. So what this means then is actually you can hear stuff happening farther away. So during the day, you normally wouldn't be able to hear something that's really, really far away, but as the day cools off and as you get closer to nightfall, or in the evening, you'll find that you're able to hear things happening farther away. Now let's take a look at this morning situation again, but let's draw several waves. And also, let's have a temperature inversion. Now, the ground itself is going to block certain paths by reflecting the sound up. This creates a shadow zone. Where it would be very hard to hear sounds from the source. And this kind of also helps explain why the mornings would be kind of quiet. Also, in the morning, we tend to have this temperature inversion because the ground is still cool from being at night, and then suddenly the air starts warming up from the sun. So we would have another one of these kind of inversions here, and mornings tend to be kind of quieter. Now, there's going to be times when you wake up in the morning and you're able to hear distant noises. This, again, happens during a temperature inversion. And this also means that you're going to be in for a hot day. Inversions are unusual in the morning, but they do happen. During a typical day, cooler air is above the warmer air next to the ground. Convection then has the warmer air traveling upwards, giving people on the ground a cooling effect. These convection currents also take smog and other pollutions away from the ground, which is nice. If there's an inversion during the morning, the cool air is next to the ground and the warm air is higher up. This means the air next to the ground will not rise and the air next to the ground stays stagnant. Over the course of the day, that air will warm up and it will keep all of the smog and pollutants near the earth. So it's kind of not a very nice type of day. But you're in for an inversion if you can hear sounds farther from you than you normally would. All right, that's going to conclude video 2.